Let's study the on-chip black hole of Xi and collaborators. This is the paper titled Quantum Simulation of Hawking Radiation and Curved Spacetime with a Superconducting On-Chip Black Hole. Archive 2111.11092, published in Nature Communications in 2023. George, before we touch a single equation, tell me why this one is special in the whole stack of black hole analog papers.
Because this is the one where the quantum simulation was actually performed on a chip. Most of the black hole analog literature lives in classical or semi-classical media, shallow water in a flume, sound waves in a flowing Bose-Einstein condensate, light in an optical fiber. Beautiful experiments, but the quantumness is either indirect or it's carried by a classical field. Here the horizon lives on a programmable superconducting quantum processor. 10 transmon qubits in a line with 9 tunable couplers between them. A single quantum excitation hops down that chain, and the geometry of a black hole is literally written into the pattern of hopping strengths. So when we talk about reproducing this on hardware, we mean it in the most direct possible sense. The platform is a gate model adjacent quantum computer.
And that's exactly why our listener cares. In his project, this is Pillar C, the one paper where the simulation ran on real quantum hardware, not just in a numerical solver. His hardware runs H01 on IBM, H03 on Rigetti, H06 on IonQ, are all reproductions of exactly this curved spacetime walk. So let's give him the mathematics and the experimental detail, not the hand-waving.
Agreed. Let me set the target up front so we know where we're going. There are 4 things this paper does, and each has real math behind it. 1. They build a Hamiltonian on the chip, whose single excitation dynamics is the massless Dirac equation in a curved 1 plus 1-dimensional spacetime. 2. They run quantum walks and show a wave packet getting trapped near an analog horizon. 3. They extract a thermal, Planckian, Hawking spectrum from quantum state tomography and read off an analog Hawking temperature. 4. They watch the entanglement of a Bell pair evolve inside the black hole. We'll take them in that order, and I'll spell out every relation in words.
Perfect. Start with the chip itself. What is a transmon, and what does a tunable coupler actually buy you?
A transmon is a superconducting artificial atom, a Josephson junction shunted by a capacitor. It's an anharmonic oscillator. Its energy levels are not evenly spaced, so you can isolate the lowest 2, ground and excited, call them 0 and 1, and treat it as a qubit. The transition frequency is tunable because the junction is actually a loop of 2 junctions, a squid, and threading magnetic flux through that loop changes the effective Josephson energy, which changes the frequency. In this device, the qubit frequencies sit around 4.6 to 5.3 GHz. The charging energy E sub c is about 195 to 200 MHz, and the Josephson energy E sub j is around 18 to 20 GHz. Energy relaxation times, T1, are roughly 20 to 37 microseconds.
10 of those in a row, and between each neighbouring pair sits a coupler. What is the coupler physically?
The coupler is also a transmon, same kind of tunable circuit, but stripped down. It has only a flux bias line. No microwave drive line, no readout resonator of its own. Its only job is to sit between 2 data qubits and mediate their interaction. And here's the key architectural idea from Jan and Oliver's tunable coupling scheme, reference 21 in the paper. When 2 qubits are near a coupler, there are 2 pathways for them to exchange an excitation. One is the direct capacitive coupling, call it G-direct, which is small and fixed, about 10 MHz. The other is a virtual second-order path where an excitation hops qubit to qubit. That indirect path depends strongly on the coupler's frequency, because it's a virtual process suppressed by the qubit coupler detuning.
So you tune the coupler's frequency and you tune how strongly the 2 qubits talk. Can you write the effective coupling out?
Yes, and this is the heart of the hardware. Start from the full circuit Hamiltonian, qubits, couplers, and all the near-neighbor exchange interactions. Every element is a weakly anharmonic oscillator, So the bare Hamiltonian for each is omega times b dagger b plus 1/2 alpha times b dagger bb, where omega is the frequency, alpha is the anharmonicity, and b dagger are the ladder operators. Then, because the qubit coupler coupling G is much smaller than the qubit coupler detuning, that's the strong dispersive condition, Ga much less than the magnitude of delta, you do a Schrieffer-Wolff transformation. That's a unitary rotation that perturbatively eliminates the coupler as a real excitation and leaves you with an effective qubit-only Hamiltonian.
And the result?
The effective qubit-qubit coupling, call it G effective between qubit J and qubit J plus 1, comes out as G effective equals G direct plus the product of the two qubit coupler couplings, G of qubit J to coupler times G of qubit J plus 1 to coupler, divided by a quantity called capital lambda. And capital lambda is the harmonic mean of the two detunings. It's 2 divided by open paren, 1 over the detuning of qubit J from the coupler, plus 1 over the detuning of qubit J plus 1 from the coupler, close paren. Now watch the sign. If you park the coupler frequency above both qubit frequencies, both detunings are negative, so capital lambda is negative. That means the second term, the virtual term, is negative and it fights the positive direct term.
So as you sweep the coupler down toward the qubits,
The virtual term grows in magnitude. You pass through a special point where it exactly cancels the direct coupling, G effective equals 0. They call that the decoupling point. Push further and G effective goes negative and keeps growing in magnitude. So the effective hopping is continuously tunable from positive through 0 to negative, just by moving one flux bias. That sign change is not a decoration. It is the whole reason a black hole horizon can exist on this chip. Hold that thought.
that's a beautiful detail, and it's exactly the knob our listener's simulations model. His R04 sim is literally called geometry as hopping. The curved metric is nothing but the ramp in coupling strength. She's chip realizes that ramp physically with the couplers. So when our listener sets a kappa sub J profile in code, she set the same profile by choosing 9 coupler flux biases. Same object, 2 substrates.
Exactly right, and it's worth dwelling on how they actually pin those biases, because reproducing this is a calibration problem before it's a physics problem. The coupler has no readout, so you can't measure it directly. They excite one neighbor qubit and watch the AC Stark shift on the other neighbor to map out the coupler spectrum. They fit a 3-body Hamiltonian, qubit, coupler, qubit, to extract the qubit coupler couplings, which are large, around 85 to 98 MHz. Then to get the effective coupling itself, they do a swap experiment. Put one excitation on qubit J, watch it slosh to qubit J plus 1, and the oscillation frequency of that population swap is twice G effective. Fourier transform the swap signal, read the peak, and you have the magnitude of G effective as a function of coupler flux. They even map both decoupling points where it crosses 0.
So the recipe is pick the coupling you want, invert the calibration curve, get the flux, load it as a Z pulse. Let me pause us there because I want to move from the box to the physics. We have a chain where we can dial each hopping to any value, positive or negative. Now, how does that become a curved spacetime?
This is the conceptual core, and it comes from a theory paper by Yang, Liu, Zhu, Luo, and Kai, reference 20 in the main text. The starting point is a Dirac field in 1 + 1 dimensions, one space, one time, living on a curved background. The general covariant Dirac equation is I times gamma, a times E mu a times the partial derivative with respect to mu of psi, plus a spin connection term minus m psi equals 0. Here gamma A are the Dirac matrices in 2 dimensions chosen as gamma 0 equals sigma z and gamma 1 equals I sigma I. Mu A is the Vielbein, or dyad in 2 dimensions, which encodes the metric. M is the mass, and psi is the 2-component spinor. We're going to take the massless limit, m going to 0, because a massless field is what propagates on light cones, and light cones are what horizons bend.
And the metric, what black hole are we putting in?
A general static 2-dimensional black hole. In Schwarzschild-like coordinates, the line element is ds squared equals f of x times dts squared minus 1 over f of x times dx squared. The single function f of x carries all the geometry. The horizon is where f of x equals 0. Call that position x sub h, with the derivative f prime at the horizon positive. Outside, f is positive. Inside, f is negative. That sign flip of f across the horizon is going to become the sign flip of the hopping. Now, they don't actually use these Schwarzschild coordinates for the simulation. They transform to what are called advanced Eddington-Finkelstein coordinates.
Why change coordinates? What's wrong with Schwarzschild?
Schwarzschild coordinates are singular at the horizon. The 1 over f blows up. Eddington-Finkelstein coordinates are regular across the horizon, and they do something else clever that's perfect for this experiment. You define a new time t equals ts plus the integral of 1 over f dx. In these coordinates, the metric becomes beautifully simple. ds squared equals f of x times dt squared minus 2 dt dx. No inverse f anywhere. Now here's the payoff. In flat space, a wave equation has two solution families: an outgoing wave and an infalling, advanced wave. When you write the wave equation in these advanced coordinates and impose that the field vanishes at infinity, the infalling mode loses its propagator entirely. It becomes a boundary condition, not a dynamical thing. So these coordinates act as a selector. They keep only the outgoing modes.
And Hawking radiation is an outgoing energy flux, so the coordinates are tuned to exactly the physics you want to see.
Precisely. That's why the paper can get away with simulating only outgoing modes. The coordinate choice is doing the filtering for you. It also has a consequence we'll need later. Because only outgoing modes exist, the interior and the exterior of the black hole behave equivalently in the simulation. A particle inside tunneling out looks the same as the walk you'd get preparing it outside. Keep that in your pocket.
Okay, we have the Dirac field, massless, on this Eddington-Finkelstein black hole. Now discretize it onto the chain.
You put the field on a lattice with spacing d, sites labeled by j, position x sub j equals open paren j minus jh, close paren times d, so the horizon sits at site jh. The massless 1+1 Dirac field, once discretized, maps onto a tight binding hopping model, and after a Jordan-Wigner transformation, onto an XY spin chain. The Hamiltonian, equation 2 in the paper, is h equals minus the sum over j of kappa sub j times, open paren, sigma plus on site, j times sigma minus on site, j plus 1, plus sigma minus on site, j times sigma plus on site, j plus 1, close paren, minus the sum over j of mu sub j, times sigma plus on site j times sigma minus on site j. Here, sigma plus and sigma minus are the qubit raising and lowering operators. Kappa sub j is the site-dependent hopping, and mu sub j is an on-site potential, a local energy offset.
Let me make sure I can rewrite that in the form our listener actually loads onto a gate machine. That hopping term, sigma plus j, sigma minus j plus 1 plus its conjugate, is an xx plus yy interaction, right?
Exactly, and this identity is worth saying slowly because it's the bridge to gate-based hardware. Sigma plus on j times sigma minus on j plus 1 plus sigma minus on j times sigma plus on j plus 1 equals 1/2 times open paren x on j times x on j plus 1 plus y on j times y on j plus 1, close paren. So the hopping Hamiltonian is equivalently h equals the sum over j of kappa sub j over 2 times open paren xj plus 1 plus yj plus 1, close paren, up to the overall sign which you can absorb. That is exactly the I-swap type, or XY interaction. On IBM, on Rigetti, on IonQ, you trotterize that. You compile each XX plus YY term into native 2-qubit gates and step through time. So Xi's analog evolution and your listener's H01, H03, and H06 digital reproductions are the same Hamiltonian. H equals sum of kappa j times XX plus YY over 2, realized two different ways.
One more foundational thing before we make it curved. The paper keeps switching between spins, fermions, and bosons. XY model, spinless, Fermi Hubbard, Bose Hubbard. Why all three, and does our listener need to worry about which one he's simulating?
Good instinct, because it can look like sleight of hand and it isn't. Here's the logic. A massless scalar field discretizes to a Bose-Hubbard model. A massless Dirac field discretizes to a spinless Fermi-Hubbard model. But both of those, in one dimension, map onto the same XY spin chain. That's the Jordan-Wigner transformation. Jordan-Wigner writes the spin-raising operator sigma plus on site J as a fermion creation operator C dagger J dressed with a string, the exponential of I pi times the sum of the fermion numbers on all sites to the left of J. That string is what enforces fermionic anti-commutation out of spin operators. Under it, the XY hopping Hamiltonian becomes exactly a free spinless fermion hopping Hamiltonian. H equals minus the sum of kappa sub J times open paren C dagger J Cj plus 1 plus Cj C dagger J plus 1 close paren minus the on-site term.
So on the chip, the qubit excitation is really a Jordan-Wigner fermion.
For the single excitation dynamics, yes. And here's the crucial simplification for your listener. With only one excitation on the chain, the Jordan-Wigner string never bites, because there's nothing to its left to count in a way that changes the sign of a nearest neighbor hop. So a single spin excitation and a single spinless fermion evolve identically. That's why the fermion versus boson distinction only shows up in the statistics of the Hawking spectrum, Fermi-Dirac versus Bose-Einstein, and not in the walk itself. His hardware runs, being single excitation, don't have to implement any string. The plain XX plus YY hopping is already the Dirac fermion. That's a real gift of working in the one-particle sector.
Good. Now the crucial question, what makes kappa sub J curved? How does the metric function f get into the hopping?
Through the discretization of the field equation, and it's a clean derivation. Take the Heisenberg equation of motion for the fermion operator C sub J. I times d by dt of Cj equals minus kappa J, Cj plus 1, minus kappa J minus 1, Cj minus 1, minus mu Cj. Now make a substitution. Define a rotated operator C tilde J equals minus I to the power J times e to the minus I mu t times Cj. That factor of minus I to the j is a standard trick in these lattice Dirac constructions. It's what converts a nearest neighbor hopping into a discrete first derivative. After substituting, the equation becomes d by dt of C tilde j equals minus kappa j, C tilde j plus 1 plus kappa j minus 1, C tilde j minus 1.
So the two neighbours now come in with opposite signs. That's a derivative structure.
Right, a symmetric difference. Now you identify the operator C tilde j with a continuum field phi at position xj, and you posit that the hopping is a sampling of the metric function. Kappa sub j equals open paren, f evaluated at xj plus 1, plus f evaluated at xj. Close paren divided by 8d, which for smooth f is approximately af evaluated at xj plus d over 2, divided by 4d. Plug that in, take the continuum limit d going to 0, Taylor expand, and the difference equation becomes a partial differential equation. The time derivative of phi equals minus f over 2 times the space derivative of phi minus f prime over 4 times phi.
And that is the massless Dirac equation in the curved metric.
It is exactly one component of it. If you decompose the Dirac spinor into two pieces and take the massless limit, you get precisely that equation. Time derivative of phi equals minus f over 2. Space derivative of pi I minus f prime over 4 phi. So the site-dependent hopping kappa sub j proportional to f evaluated near site j is the metric. The geometry is the coupling profile. There is no separate gravity on the chip. Gravity is the spatial pattern of how fast excitations are allowed to hop.
Let me extract the single most important physical statement from that equation. The coefficient in front of the space derivative is f over 2. That's a local propagation speed.
That's the whole game. Read off the effective speed of light. C effective at position x is f of x over 2 proportional to the local hopping. Where F is large, excitations move fast. Where F shrinks, they slow. And at the horizon, where f of xh equals 0, the effective speed of light goes to 0. The light cone closes. An excitation approaching the horizon slows asymptotically and cannot cross in finite lattice continuum time. That is the analog event horizon, a place where the local speed of light, set by the hopping, drops to 0.
And the sign flip of F, inside F is negative. That's the interior.
Yes. Outside F positive, kappa positive, inside F negative, kappa negative, and right at the horizon site, kappa passes through 0 and reverses. Now you see why the tunable coupler's ability to go from positive through 0 to negative was non-negotiable. A device that could only make positive couplings could still fake the trapping. The paper notes that using the absolute value of kappa gives equivalent lattice dynamics. But to faithfully map the metric components, including F changing sign, you need genuinely sign-tunable hopping. Their couplers deliver it.
Now let's get concrete about their actual choice of geometry. What F did they pick, and what are the numbers?
They chose f of x equals beta times hyperbolic tangent of etax all over eta. Beta and eta are constants. Eta has units of 1 over length, so eta controls how sharply the metric varies from one lattice site to the next. Feeding that into the hopping formula gives equation 3. Kappa sub j equals beta times hyperbolic tangent of open paren j minus jh plus 1/2 times etad close paren divided by 4 etad. Their parameters, jh equals 3, so the horizon is at qubit 3. Eta times d equals 0.35, and beta over 2 pi is about 4.39 megahertz. That tangent profile goes smoothly from negative on the left to positive on the right, crossing 0 at qubit 3. So qubits 1 and 2 are the interior of the black hole, qubit 3 is the horizon, and qubits 4 through 10 are the exterior, outer space.
Why tangent specifically?
2 reasons. First, it's smooth and it flips sign, which is what a well-behaved F near a simple horizon looks like. Near the horizon F is approximately linear. F approximately equals F prime at h times open paren, x minus xh, close paren, and tangent is linear near its 0. Second, tan saturates to constants far away, so the space-time is asymptotically flat on both sides. The excitation behaves like a free massless particle far from the horizon. And this F has genuine non-zero curvature. They note the Riemann curvature tensor is non-vanishing, so it's a real two-dimensional curved spacetime, not a coordinate trick.
They also build a flat space-time control. That's just constant hopping.
Constant hopping, kappa over 2 pi about 2.94 megahertz, uniform across the chain. Flat metric, uniform light cone. That's the baseline they compare everything against. And it's the same control your listener would run first on any hardware platform to check the walk is behaving before he turns on the curvature.
Let me take stock before we run the experiment. We have a 10-qubit chain. We've written the hopping profile so that the effective speed of light dips to 0 at qubit 3. Now put one excitation on the chip and let it walk. What do we see?
First, how they run it. They prepare an initial state. For the simplest case, that's the state where qubit 1 is excited and all others are in ground. Written 10000000000. Then they quench. They apply rectangular Z pulses to bring all 10 qubits into resonance at a common reference frequency, around 5.1 gigahertz, so that only the hopping terms matter. Being on resonance kills the on-site energy differences. Simultaneously, the couplers are biased to give either the curved kappa profile or the flat constant. The state evolves under Schrödinger's equation, ESI of t equals e to the minus iht, acting on c psi of 0. After a chosen time t, they bias the qubits back and read out. The observable is the site occupation, p sub j of t, which is the expectation value of sigma plus j sigma minus j in the evolved state, the probability that qubit j is excited. They average 5,000 single-shot measurements per point.
And the flat case looks like a textbook quantum walk.
Exactly, a ballistic light cone spreading. The excitation fans out symmetrically, a linear light cone in the space-time heat map, reflecting off the chain boundaries at qubit 1 and qubit 10. That's the standard continuous time quantum walk, and it matches earlier superconducting quantum walk work. Nothing traps it. The cone has a constant opening angle because the speed is uniform.
Now switch on the curvature.
Completely different picture. With the tan profile, an excitation started at qubit 1, inside the horizon, is largely trapped. It piles up near the horizon at qubit 3 and mostly cannot get across. The light cone bends over and nearly closes as it approaches qubit 3, exactly as the vanishing effective speed of light predicts. In the space-time heat map, you see the trajectory curl toward the horizon and stall, instead of spreading freely. That bending of the light cone is the direct visual signature of the curved metric.
They test a few initial positions, right?
4 initial states. 1 excitation at qubit 1, deep interior. 2 excitations, qubits 1 and 2. 1 excitation at qubit 3, right on the horizon, and 1 at qubit 4, just outside. The interior and just outside cases look equivalent, which is that outgoing mode property we flagged. Because the Eddington-Finkelstein coordinates keep only outgoing modes, inside tunneling out and outside walking are the same physics, and the on-the-horizon case is the most delicate.
What happens to a particle born exactly on the horizon?
In the ideal continuum, it's stuck forever. The couplings on both sides of the horizon vanish, so it's pinned. On the finite lattice, the couplings adjacent to the horizon are small, but not exactly zero, about 0.54 MHz. So the excitation looks localized at qubit 3 for a while, then slowly leaks away. That leakage is a finite size effect, and they're careful to say so. In a 300-site simulation, the pinning lasts far longer. As the lattice spacing goes to 0, the trapping becomes permanent, which is the correct horizon behavior.
How do they quantify that the walk is right, not just that it looks right?
Fidelity between the measured occupation distribution and the theoretical one. They define f of t as the sum over sites j of the square root of open paren p measured j times p theory j close paren. That's the classical Bhattacharya-style fidelity between two probability distributions over sites. They report it stays above 97% within 400 nanoseconds of evolution. So the curved spacetime walk is reproduced to better than 3% for the whole window before boundary reflections and decoherence matter. That's a strong number for a 10-qubit analog evolution.
This is the piece our listener's R04 sim reproduces numerically. The geometry as hopping walk, the light cone bending, the trapping, and his H01, H03, H06 runs reproduce it on gate hardware. So if he wants a cross-check, the 97% site fidelity over 400 nanoseconds is the bar she set with an analog chip. A trotterized digital run should aim to match the same trapping and light cone bending.
And I'd add a practical note for reproduction. The 400 nanosecond window is bounded by 2 things. Defacing. Their T2 echo times are single-digit to mid-teens microseconds, so coherence isn't the limit here. And boundary reflection of qubit 1 and qubit 10. On a digital platform, the analog of that window is trotter depth versus 2-qubit gate error. He'll hit gate error limited depth long before coherence, so the trapping signature has to be visible in relatively few trotter steps. The good news is, the trapping is a low-frequency, robust feature. It shows up early.
Before Hawking radiation, help me place this device among the other analog horizons. Why is a superconducting chip a genuinely different kind of experiment from water waves or a Bose-Einstein condensate?
3 distinctions matter. First, the medium is quantum and controllable at the single quantum level. In a flume, the horizon is a hump in a classical water flow, and the field is a classical surface wave. In a flowing condensate, the horizon is where the flow goes supersonic, and the field is a phonon. Those are magnificent experiments, but here the excitation is a single qubit quantum, and every site is individually measurable and preparable. Second, programmability. The metric is not fixed by fluid dynamics, you dial it. You can put the horizon at site 3, or in the center with 2 horizons, or make it flat, all on the same chip in the same afternoon, by reprogramming coupler fluxes. No other analog platform lets you rewrite the spacetime that freely. Third, the temperature scale. Because couplings are megahertz, the analog surface gravity is around 10 to the fifth hertz, and the Hawking temperature is around 10 to the minus 5 Kelvin. 5 to 7 orders of magnitude hotter than water or condensate horizons.
And hotter is good because
The Hawking signal is exponentially small in energy over temperature. A hotter horizon means the thermal occupations are larger and less buried under noise, so you can actually resolve the spectrum with tomography. The flip side, which the paper is honest about, is that a hotter, smaller analog corresponds to a tiny black hole, about 10 to the minus 3 solar masses equivalent, whereas the condensate analogs sit at hundreds of solar masses. Neither is a real astrophysical black hole. The point is only that the surface gravity to temperature relation, T equals GH over 2 pi, holds across all of them. That universality across wildly different platforms is itself the deep statement.
which is exactly why our listeners' cross-platform reproductions matter. He's testing that same universality across qubit technologies. Okay, let's go to the headline, Hawking radiation. Walk me from the geometry to a temperature. And I want the tunneling derivation, because that's the part people wave their hands through.
We'll do it properly. The claim to establish is equation 4. The probability of radiation outside the horizon is proportional to e to the minus e over th, a Boltzmann factor, where e is the energy of the emitted particle and th is the Hawking temperature. And th is set by the surface gravity. Let me define surface gravity first. G sub h equals 1/2 times f prime evaluated at the horizon. For their tanh metric, f prime at the horizon is beta, so G sub h equals beta over 2. That single number controls the temperature.
Start the tunneling calculation.
We follow the Damour-Ruffini and Parekh-Wilczek tunneling picture. Consider an outgoing mode of positive energy omega, positive as seen by an observer at infinity, for a massless field. In Schwarzschild coordinates, that mode is proportional to the exponential of minus I omega times, open paren, ts minus the integral of dx over f of x, close paren. The integral of 1 over f is where the horizon physics hides, because f vanishes there. Near the horizon, f of x is approximately 2gh times, open paren, x minus xh, close paren. That's just f prime at h times the displacement, and f prime at h is 2gh. So the integral of dx over f splits into a smooth part, call it capital F of x, plus a singular part, 1 over 2gh, times the natural log of the absolute value of x minus xh.
So the mode picks up a logarithm at the horizon.
Right. Converting to the Eddington-Finkelstein time, the outgoing positive energy mode becomes proportional to e to the minus I omega times, open bracket, t minus 2f of x, close bracket, times the absolute value of x minus xh, raised to the power I omega over gh. That last factor, modulus of x minus xh to the power I omega over gh, oscillates infinitely fast as you approach the horizon. It's not smooth across xh, so you can't just continue it naively from outside to inside. You continue it analytically, going around the singularity in the complex plane.
And that analytic continuation is where the temperature is born.
Yes. When x crosses from outside the horizon to inside, the log of the absolute value of xh minus x picks up an imaginary part of minus I pi. You go halfway around the branch point in the complex plane. So the factor modulus of xh minus x to the power I omega over gah acquires a real multiplicative factor of e to the pi omega over gh. Now compare the amplitude of the mode inside versus outside. The ratio of probabilities, outside relative to inside, is the modulus squared of that continuation factor, which gives the tunneling rate, capital P equals e to the minus 2 pi omega over gh. That is the barrier penetration probability for a single particle of energy omega across the horizon.
And that exponential is already a thermal Boltzmann factor.
It is. Read it as e to the minus omega over t, with the temperature T equal to gh over 2 pi. But to get an occupation number, a full Bose-Einstein or Fermi-Dirac spectrum, you sum over multi-particle processes. For bosons, the probability of emitting k quanta of energy omega goes as capital P to the K. 1, P, P squared, P cubed, and so on. The mean occupation number is the sum over K of K times P to the K, divided by the sum over K of P to the K. That geometric series gives n of omega equals 1 over open paren e to the 2 pi omega over gh minus 1 close paren. A Planck spectrum, 1 over e to the omega over t minus 1, with t equals gAh over 2 pi.
And for fermions, which is what a qubit excitation actually is?
For fermions, the Pauli principle caps the occupation at 1. You can have 0 or 1 particle of a given energy, with probabilities 1 and p. So the mean occupation is the sum over k equals 0 and 1 of kp to the k, over the same sum without the k, which is p over 1 plus p equal to 1 over open paren e to the 2 pi omega over gh plus 1 close paren. A Fermi-Dirac distribution, 1 over e to the omega over t plus 1, with the same temperature, T equals gh over 2 pi. Either way, the temperature is surface gravity over 2 pi. That is the Hawking temperature, and it fell out of nothing but analytic continuation of an outgoing mode across the horizon.
That detailed balance language shows up too. Same thing?
Same thing from a thermodynamic angle. The ratio of the rate to create a particle to the rate to annihilate it across the horizon is e to the minus omega over t. That's detailed balance in a thermal bath at temperature T. The interior and exterior exchange particles and energy through the horizon like a grand canonical system, and the Bose and Fermi occupations are just the equilibrium statistics of that exchange. And I should connect it to the more familiar pair creation cartoon. A particle-antiparticle pair forms near the horizon, the negative energy partner falls in and annihilates a particle inside, and a positive energy particle escapes to infinity. The tunneling picture and the pair creation picture are the same physics. A negative energy antiparticle falling in is equivalent to a positive energy particle tunneling out.
Now let's get the number for this chip. Surface gravity is beta over 2. Temperature?
Th equals gAh over 2 pi equals beta over 4 pi. In their frequency units, Th over 2 pi works out to beta over 8 pi squared, which is about 0.35 megahertz. Convert that frequency to a physical temperature with Planck's constant over Boltzmann's constant. T in Kelvin equals Planck, h times the frequency over Boltzmann k. And 0.35 megahertz corresponds to about 1.7 times 10 to the minus 5 Kelvin. So the analog Hawking temperature is roughly 17 microkelvin. That's the ideal, noise-free value.
Put that in context against other analog black holes.
This is one of the nicest points in the paper. The Hawking temperature scales with the surface gravity, which scales with the characteristic frequency of your platform. Shallow water waves give surface gravities of order tenths of a hertz and temperatures around 10 to the minus 12 Kelvin. Bose-Einstein condensates give tens to hundreds of hertz, temperatures around 10 to the minus 10 to 10 to the minus 9 Kelvin. Superconducting qubits operate at megahertz couplings, 5 orders of magnitude higher, so the surface gravity is around 10 to the 5th hertz and the Hawking temperature is around 10 to the minus 5 Kelvin. It's the hottest analog horizon of the bunch, which paradoxically makes the radiation easier to resolve. If you map it to a real Schwarzschild black hole of the same temperature, the equivalent mass is about 10 to the minus 3 solar masses, whereas the BC analogues correspond to hundreds of solar masses.
So higher temperature means the thermal signal is bigger relative to the noise. Now, how do they actually measure the spectrum? This is where on a chip gets serious.
This is the experimental crown jewel, quantum state tomography. They prepare a single excitation inside the horizon, qubit 1 excited, everything else ground, and evolve for a long time, 1,000 nanoseconds. That's long enough that whatever is going to tunnel out has tunneled out, but short enough that boundary reflections haven't corrupted the exterior. Then they perform full quantum state tomography on the 7 qubits outside the horizon, qubits 4 through 10. Tomography means reconstructing the entire 7-qubit density matrix, RO out, by measuring in many bases and inverting. 7 qubits is a 128-dimensional Hilbert space, so this is a serious measurement.
And from that density matrix, they pull out radiation probabilities. How?
They take the reconstructed exterior density matrix, embed it back into the full 10-qubit space by setting the 3 unmeasured qubits to ground, and then project onto the energy eigenstates of the full Hamiltonian. If E sub n is the nth eigenenergy and the eigenstate is ket En, then the probability of finding a particle of energy, En outside the horizon, is P sub n equals bra En, RO out, ket En, the diagonal matrix element of the measured density matrix in the energy basis. That's the occupation of each energy level.
There are over 1,000 eigenstates for 10 qubits. Which ones matter?
10. The Hamiltonian conserves total excitation number. The hopping moves an excitation but never creates or destroys one. So starting from one excitation, you stay in the single excitation sector, which has exactly 10 eigenstates, one per site's worth of superposition. All the P sub n for multiparticle or zero-particle states are 0. So of the 1024 eigenvalues, only the 10 single-particle ones carry radiation probability. That's a huge simplification, and it's why 7-qubit tomography is even tractable as a spectrum measurement.
Then they plot those probabilities against energy.
They take the single-particle eigenstates with positive energy. Those are the genuinely radiated outgoing modes, and they average the probabilities of states at the same energy, calling that P bar sub n. Then they plot the logarithm of P bar n against the energy En. If the radiation is thermal, equation 4 says P bar n is proportional to e to the minus En over Th, so the log of P bar n should be a straight line in En with slope minus 1 over Th. And that's what they see. The log of the average radiation probability is approximately linear in energy. The slope gives the temperature. The ideal simulation slope corresponds to that 1.7 times 10 to the minus 5 Kelvin. The experimentally fitted temperature is about 7.7 times 10 to the minus 5 Kelvin.
That's a factor of 4 or 5 off. Is that a problem?
They're honest that it's the same order of magnitude, not a precision match, and they diagnose why. The dominant error is the imperfect initial state. The fidelity between the actual prepared initial state and the ideal one is 99.2%. Sounds high, but the radiated probabilities are tiny. So small state preparation errors plus XY crosstalk, thermal excitation and leakage distort the high-energy tail of the spectrum, where the probabilities are smallest. When they substitute the measured imperfect initial state into the numerical simulation instead of the ideal one, the simulation and experiment agree much better. So the deviation is understood, and it's not a failure of the thermal picture. The low-energy part of the spectrum, where the signal is strongest, is clean and linear. The high-energy divergence is noise.
That's an important honesty point for our listeners' R06 and R07 Hawking thermometry sims. His numerics can reproduce the ideal straight line. The value of doing it on hardware, like Shy, is precisely to see where and how the noise bends the tail.
And it tells him what to control. If he reproduces the tomography to spectrum pipeline on IBM or IonQ, the temperature he fits will be corrupted in the same way. By state prep and readout error, inflating the small high-energy probabilities. The mitigation is exactly what Shay did. Characterize the real prepared state and propagate it through the model rather than assuming the ideal input. His R07 thermometry sim should fit the slope only over the low-energy, high-signal window, and quote the high-energy divergence as a noise diagnostic, not average it in.
7-qubit tomography is expensive. How many measurements is that, and is it the bottleneck for reproduction?
Full tomography scales badly. You measure in a set of bases that spans the operator space, and for 7 qubits, the naive Pauli basis count is 3 to the 7th, over 2,000 settings, each repeated thousands of times. Then you invert to reconstruct a 128 by 128 density matrix, usually with a maximum likelihood fit to keep it physical. That's the real experimental cost of the radiation measurement, far more than the walk. But there's a shortcut your listener should exploit. Because the dynamics conserves excitation number and he starts with one excitation, the state lives in a tiny subspace, the vacuum plus the single particle sector. He doesn't need the full density matrix. He needs its overlap with 10 single-particle eigenstates. So excitation number restricted or subspace tomography, or even just measuring the relevant correlators, collapses the cost enormously. Sure did full tomography for rigor. A smart reproduction can measure far less and still get the spectrum.
And the readout chain itself, anything there that shapes the result.
Yes, and it's why the high-energy tail is noisy. All 10 qubits share one readout line with a Josephson parametric amplifier and a HEMT amplifier. Their single qubit readout fidelities are around 94 to 98% for ground and 87 to 91% for the excited state. Those excited state readout errors are the dominant contamination of the tiny radiation probabilities. A false excited state count looks exactly like a radiated particle. So readout error mitigation, a calibrated confusion matrix inverted out of the raw counts, is essential for a faithful temperature. That's true on his gate machines too. The small p-bar n values at high energy are precisely where readout bias dominates, so he must mitigate before he fits the slope.
There's also a monotonic rise signature they highlight, P out, increasing in time. Explain that one, it's simpler.
It's the coarse signature that complements the fine spectrum. Define P out as the sum of occupations over the exterior qubits, 4 through 10. Start with the particle inside. P out is near zero. As the system evolves, the particle tunnels across the horizon, and P out rises with time. That rising exterior probability is the black hole evaporating, leaking its particle to the outside. Many analog experiments use exactly this rising transmission signature as the primary evidence of Hawking emission. The spectrum is the refined follow-up that shows the rise is thermal, not just any leakage.
Now the word stimulated, they're very careful to say this is stimulated, not spontaneous Hawking radiation. Why and does it matter?
It matters a lot for honest scope. Spontaneous Hawking radiation is emission out of the vacuum. No particle present, the horizon spontaneously creates the pair. That's what Steinhauer's Bose-Einstein condensate experiments claim to see, and it's the genuinely quantum vacuum fluctuation effect. In this chip experiment, they seed the process. They put a real excitation inside the horizon by flipping a qubit to the excited state and then watch it tunnel out. That's stimulated emission. The presence of the initial particle induces the outgoing flux. The spectrum is still thermal, governed by the same surface gravity temperature, and the tunneling calculation is identical, but it is not vacuum emission. So the claim is they observe the thermal, Planckian character of horizon emission in the stimulated regime on a quantum processor, which is itself a first for the superconducting platform and the first realization of Jacobson's lattice black hole idea. They don't claim spontaneous vacuum radiation.
That lineage is nice. Corley and Jacobson's lattice black hole from the late 1990s finally instantiated.
Right. Jacobson's motivation was the trans-Planckian problem. Hawking's derivation seems to rely on arbitrarily high frequencies right at the horizon, which is physically suspect. Putting the field on a lattice imposes a shortest wavelength, the lattice spacing, which cuts off those trans-Planckian modes and lets you ask whether Hawking radiation survives. This experiment is a physical lattice with a physical short-distance cutoff, showing the thermal spectrum still emerges. That's conceptually satisfying, and it's why the discretization isn't just a numerical convenience. It's part of the physics being tested.
Let's move to the fourth result, entanglement. They put a bell pair inside the black hole and watch it. What's the setup, gate by gate?
They prepare an entangled pair on qubits 1 and 2, both inside the horizon. The target state is the Bell state, open paren, 0, 0 plus 1, 1, close paren, over root 2. The circuit is parallel single qubit rotations, a Y rotation by plus pi over 2 on one qubit and by minus pi over 2 on the other. Then a controlled Z gate, which is the diagonal gate that flips the sign of the 1, 1 component. Then a final Y rotation by pi over 2 on one qubit. That sequence produces the Bell pair with a measured preparation fidelity of about 99.2%. They quote a mean of 99.15%. Then they quench into either the flat or the curved spacetime and do time-dependent tomography on the 2-qubit state. reconstructing Rho of T at each time.
And from Rowan, they compute two things, entropy and concurrence. Define both.
The entanglement entropy first. The total system, the two interior qubits plus everything else, stays in a pure state throughout the coherent evolution. For a pure global state, the entanglement between a subsystem and its complement is the von Neumann entropy of the subsystem's reduced density matrix. S of RHO equals minus the trace of RHO times the log of RHO. And because the global state is pure, the entropy of the interior pair equals the entropy of the rest. S of ROin equals S of a rho rest. Measuring the two interior qubits is far cheaper than measuring the other 8, so they compute S of ROin as the entanglement measure. It quantifies how entangled the interior pair is with the exterior.
And concurrence?
Concurrence is Wouter's measure of the entanglement specifically between the two interior qubits with each other, a 2-qubit entanglement monotone. You compute it from Rho-in as follows. Form the spin-flipped state Rho tilde equals open paren sigma e tensor sigma I, close paren, times Rho-in complex conjugated, times open paren sigma e tensor sigma E, close paren. Then take the matrix Rho-in times Rho tilde, find its eigenvalues, take their square roots and sort them in decreasing order as lambda 1, lambda 2, lambda 3, lambda 4. The concurrence is the maximum of 0 and open paren lambda 1 minus lambda 2 minus lambda 3 minus lambda 4, close paren. Concurrence 1 is a maximally entangled pair. 0 is unentangled.
So entropy measures interior versus exterior entanglement. Concurrence measures the two interior qubits' entanglement with each other. What happens in the two spacetimes?
Two complementary stories. The entanglement entropy of the interior pair increases progressively in the curved case because Hawking radiation is carrying entanglement across the horizon. Each escaping particle is entangled with its partner left behind, so interior-exterior entanglement builds up over time. That's the microscopic engine behind Hawking's statement that black hole entropy grows as it radiates. In the flat case, the entropy instead shows two wavefronts from quantum interference and reflection, rather than a steady climb. Meanwhile, the concurrence, the entanglement between the two interior qubits, decreases in both cases, because the pair's coherence bleeds out into the larger system. But, and this is the pretty part, the concurrence decays more slowly in the curved case.
Why slower in the curved case?
Because the analog gravity near the horizon throttles propagation. The effective speed of light is suppressed near qubit 3, so the entanglement can't leak outward as fast. The horizon partially protects the interior pair's mutual entanglement. In flat space, there's no such barrier, so the concurrence collapses rapidly. It's the same trapping physics from the quantum walk, now expressed in the entanglement dynamics. Gravity slows the loss of correlations. So one experiment, one Bell pair, and you see both the growth of interior-exterior entanglement, which is the informational side of Hawking radiation, and the gravitational protection of interior correlations.
George, this is the moment to be scrupulously honest. What does this experiment actually establish about real black holes, and what does it not?
Let me draw the line clearly, because our listener should not overclaim when he reproduces it. What it establishes, that a controllable quantum system with a position-dependent hopping profile realizes, to high fidelity, the kinematics of a massless field on a two-dimensional curved background with a horizon. The light cone bending, the trapping, and crucially a thermal emission spectrum whose temperature is fixed by the surface gravity through T equals gh over 2 pi. The mathematics of mode propagation and analytic continuation across the horizon is genuinely shared between this chip and a real black hole. That correspondence is exact at the level of the field equation.
And what it does not establish?
Several things, and the paper is candid about them. First, there's no real gravity here, no Einstein equations, no dynamical spacetime, no back reaction. The metric is a fixed, externally imposed coupling profile. It doesn't respond to the excitation. So there's no black hole evaporation in the sense of the horizon shrinking as it radiates. Second, it's stimulated, not spontaneous. They inject a particle rather than watching the vacuum radiate, so this is not a test of vacuum particle creation. Third, it's 1 plus 1 dimensional and a single excitation, a fermionic lattice model, a drastically simplified setting compared to a real 4-dimensional black hole with interacting quantum fields. Fourth, only outgoing modes are simulated by the coordinate choice. And fifth, it's finite size. The trapping is not permanent. The horizon is a leaky membrane, and reflections off the chain ends eventually contaminate everything. So the honest statement is, this reproduces the universal kinematic signatures of horizon physics, thermality set by surface gravity, in a fully quantum programmable platform. It does not resolve black hole thermodynamics, the information paradox, or quantum gravity. It's a faithful analog of the field theory on a fixed background. Nothing more and nothing less.
That's the right altitude. Now let me pull it all back to our listeners' project, because this is Pillar C, the one paper where the simulation was actually performed on hardware. Tie the threads together for him.
Here's the map. The physics object is a single Hamiltonian. H equals the sum over J of kappa sub J times open paren xj plus 1 plus yj plus 1 close paren over 2. Shai realized it in analog fashion, continuous evolution under that Hamiltonian, with the kappa sub J profile set by 9 tunable coupler flux biases. Your listener's hardware runs H01 on IBM, H03 on Rigetti, and H06 on IonQ, realized the same Hamiltonian digitally, trotterized into native 2-qubit gates on gate model machines. Same kappa sub J curved profile, the Tanch ramp, kappa sub J equals beta tan of open paren J minus JH plus 1/2 times ETD close paren over 4 ETD. That's the exact curved coupling ramp his simulations use.
So his gate-based runs are cross-platform checks of Xi's superconducting analog result.
Precisely. Xi has one data point, a superconducting analog processor. When your listener reproduces the trapping and the thermal spectrum on trapped ions, on a different superconducting architecture with digital gates, and on Rigetti, he's testing whether the horizon physics is platform-independent, whether it's really the Hamiltonian and not some quirk of transmons with couplers. That's the scientific value of the cross-platform reproduction, universality of the analog horizon across qubit technologies. And his numerical sims bracket it. R04, geometry as hopping, reproduces the curved walk and light cone bending. R06 and R07, the Hawking thermometry sims, reproduce the tomography to spectrum pipeline and the straight-line log probability versus energy fit that yields the temperature.
What's the one hardware subtlety he should watch that Xi's analog approach hides?
The sign of kappa. On Xi's chip, negative hopping is free. You just push the coupler below the decoupling point and it's genuinely negative. On a gate-based machine, you implement the XX plus YY interaction with a sign through the rotation angle in your trotter step. So a negative kappa sub J is just a negated angle, trivial. But there's a subtlety. The paper notes the lattice dynamics is actually invariant if you replace kappa by its absolute value on both sides of the horizon. Because for the occupation dynamics, only the magnitude enters the equivalent model. The sign flip is required to faithfully map the metric components, but the trapping and radiation are visible even with all positive couplings, as their supplementary shows. So if his hardware makes one sign easier, the physics signatures still come through. The place he genuinely needs the ramp, the varying magnitude of kappa sub J, is non-negotiable, because that's the varying effective speed of light. Uniform magnitude gives flat space. The Tanch magnitude gradient is the horizon.
Let me ask about the parameters he should actually load. Give him the concrete recipe.
10 sites. Horizon at site 3, so JH equals 3. Eta times D equals 0.35. Beta over 2 pi equals 4.39 MHz. Though on a digital machine the absolute frequency is irrelevant. Only the dimensionless products matter. So what he really loads is kappa sub J over beta as a function of site, times an evolution phase. Concretely, kappa sub J is proportional to hyperbolic tangent of open paren J minus 3 plus 1/2 times 0.35 close paren divided by 4 times 0.35. Evaluate that for J from 1 to 9 and you get the 9 bond strengths. Negative on the left, near zero at the horizon bond, about 0.54 MHz in their units, and saturating positive toward the right. The flat control is all bonds equal, kappa over 2 pi equals 2.94 MHz. For the total evolution, Shy went to 1000 nanoseconds times beta for the radiation measurement and 400 nanoseconds for the clean walk. In dimensionless terms, that's roughly beta times t of order a few, so a handful of characteristic hopping times.
And the observable pipeline for the temperature, restate it as a checklist.
Prepare a single excitation inside the horizon. Site 1 excited, rest ground. 2. Evolve under the curved Hamiltonian for a time long enough for tunneling but short enough to avoid boundary reflection. 3. Do quantum state tomography on the exterior qubits, sites 4 through 10. 4. Embed that density matrix in the full space with the interior qubits set to ground, and compute P sub n equals bra en ro out ket en against the single particle energy eigenstates. 5. Keep the positive energy single particle states, average probabilities at equal energy to get P bar n, and plot log P bar n versus En. 6. Fit the slope. The temperature is -1 over slope, and you compare it to beta over 4 pi. 7, and this is the honesty step, fit only over the low energy window where the signal dominates noise, and report the high energy divergence as a state preparation and readout diagnostic, not as physics.
That's a clean protocol. Before we close, is there anything in the paper's extra material worth flagging for someone doing a careful reproduction?
Few things from the supplement. First, they study disorder, random next nearest neighbor couplings, and random on-site potentials, and show the thermal spectrum is robust for the small disorder levels they actually have, next nearest neighbor coupling around 0.1 MHz and on-site variations under 0.2 MHz. Strong disorder does wash out the thermal line, so for a reproduction he should keep frequency alignment tight. Second, they simulate a 300-qubit chain to show the horizon behaves like a partially transmitting membrane, and that the reflections he'll see on 10 qubits are pure finite-size artifacts. Third, they do a continuum limit analysis with a Gaussian wave packet and derive the lattice dispersion relation. Omega of k equals 1 over 2 d times the sine of 2kd, which reduces to the linear, massless dispersion speed of light in the long wavelength limit. That dispersion relation is what guarantees the Walker really is a massless relativistic particle when the wavelength is large compared to the lattice spacing. And fourth, they show an alternative geometry with the black hole in the center of the chain, 2 horizons, which is a nice variation if he wants a second independent configuration to test universality.
George, give me the compressed version. If our listener remembers 3 equations from this whole episode, which 3?
Equation 1, the Hamiltonian. H equals minus the sum over j of kappa sub j times, open paren, sigma plus j, sigma minus j plus 1, plus sigma minus j, sigma plus j plus 1, close paren, equivalently the sum of kappa sub j over 2 times xx plus yy. That's the whole simulator. Equation 2, the geometry to hopping map, kappa sub j proportional to f evaluated near site j, which makes the effective speed of light equal to f over 2, vanishing at the horizon where f is 0. That's what makes it curved. Equation 3, the temperature, Th equals GAH over 2 pi equals beta over 4 pi, with the thermal spectrum, radiation probability, proportional to e to the minus e over Th. The Planckian line whose slope on a log plot is the black hole's temperature. Hamiltonian, geometry as hopping, thermal spectrum. Everything else is calibration and tomography.
And the one-sentence honest summary of what was achieved.
On a 10-qubit superconducting processor with 9 tunable couplers, they wrote a black hole metric into the hopping profile, watched a quantum excitation get trapped by an analog horizon, and read a thermal Hawking spectrum, temperature set by surface gravity over 2 pi, directly out of 7-qubit quantum state tomography. It's the kinematics of horizon physics, fully quantum and programmable, realized on a chip. Not real gravity, but a real quantum simulation.
And for our listener, the punchline. This is the paper his whole Pillar C exists to reproduce and cross-check. She did it once, in analog, on superconducting hardware. His job is to show the same Hamiltonian, the same tanned coupling ramp, the same trapping and the same thermal line appear on IBM, on Rigetti, on IonQ, proving the horizon lives in the mathematics, not in any one machine. George, this was exactly the level of detail he needed. Thank you.
My pleasure. And a closing tip for the reproduction. Start with the flat spacetime control and confirm a clean ballistic light cone before you switch on the tan-H ramp. If the flat walk isn't right, the curved one will lie to you. Get the uniform quantum walk perfect first, then bend the light cone. That's how Shai did it, and it's how you should too.
Perfect place to end. That was Shai and collaborators superconducting on-chip black hole, the horizon you can program, the Hawking temperature you can fit with a straight line, and the one experiment in the project that actually ran on quantum hardware. Until next time.